Russia has introduced a new missile system that could be impossible to defend against.
As we talk today, there have recently been some reports that the Chinese have a hypersonic missile.
Yeah. I don't know if it's quite a Sputnik moment, but I think it's very close to that.
CEOs of America's largest defense contractors describe this scarcity of wind tunnels as a choke point in testing.
To win the race for the world's best weapon systems and emerging technologies, the U.S. government knows it is vital to move faster than a speeding bullet. Bring on the BAM. It's the nation's new giant tool to pilot high-tech innovation at hypersonic speed. BAM, an acronym for Ballistic Aero-Optics and Materials, is the nation's largest and best-equipped facility of its kind. The enclosed range will host experimental testing of systems for hypersonic flight, for directed energy, such as laser propagation, and for materials that can withstand hypervelocity impacts. The BAM is part of the George H.W. Bush Combat Development Complex, located on the Texas A&M Rellis campus in Bryan, Texas.
As we did with the rest of BCDC, we designed the BAM range in consultation with scientists and engineers from the Department of Defense, the national laboratories, and the defense industry. Our goal was to address the most critical infrastructure needs of the nation with regards to testing and experimentation. Our vision is to go faster, to accelerate the development of new technology in support of our military, on the ground, in the air, and in space. We understand that speed is life in the military.
The BAM bridges a critical infrastructure gap between lab-scale wind tunnels and open-range testing, and the BAM offers unique advantages. Compared with lab wind tunnels, the BAM's larger scale, 8 feet in diameter and ultimately a kilometer long, allows for more realistic experiments. Unlike open-range testing, the BAM is enclosed, so researchers can leverage the world's most advanced diagnostic tools and techniques to measure weather effects and aerothermodynamics.
Until now, designers had to go outdoors to test at scale, but in the BAM range, we can test in a controlled and characterized environment. This allows us to get those precise measurements as accurately as we can. Open-range tests take 6 months or longer to prepare for and can cost tens of millions of dollars apiece. But at the BAM range, we'll be able to test weekly and at a fraction of the cost. By raising the tempo and lowering the cost, innovators can test, analyze, pivot, and repeat. They'll learn faster and reduce the risk.
So what goes on inside the BAM? It happens faster than a blink of an eye. But let's slow it down and take a look. Tests and experiments fall into 3 broad areas. Area 1 is aero-optics. When a laser propagates through the BAM, the directed beam of energy encounters simulated atmospheric disturbances, everything from rain, wind, and heat to battlefield smoke, flying debris, and helicopter downwash. Aero-optic researchers measure the impact of different disturbances to discover how to extend the range, power, and accuracy of lasers as tools to identify military targets and defend against incoming threats. Like other BAM research, the aero-optic testing also could have civilian applications. After all, lasers are used everywhere from surgical wards to checkout lines. Area 2 is hypersonics. A high-tech launcher propels a specially designed vehicle along rails that are mounted inside. The vehicle travels at speeds up to Mach 10 before it is slowed carefully for post-flight recovery and analysis. Experiments examine questions such as, at what speed does smooth, stable airflow become turbulent? How does turbulent airflow impact the incredible heat loads on the fast-moving object? The research is essential if the U.S. is to surpass China and Russia in development of hypersonic systems that can maneuver in flight. Area 3 is hypervelocity impacts. The launcher, a 2-stage light gas gun, quickly accelerates a 4-inch diameter projectile until it smashes into a target. Experiments explore how certain materials, both on the projectile and within the target, can better withstand these super-speed, high-energy impacts. Advances could protect spacecraft and astronauts from out-of-this-world debris, as well as save the lives of warfighters. As with the rest of BCDC, the BAM range comes with one more unmatched asset: Texas A&M itself. Development of the BAM range was born out of the university's prowess in national security research. The Aggie culture of national service grows out of its rich military tradition. And the Texas A&M University system has the know-how to protect sensitive research while managing projects with other universities, the government, and the private sector.
We are looking for more partners, people and teams who want to develop and accelerate new technology in service to the nation. We were made for this mission and are ready to serve. Come join us.